All right, in this video, we're going to be taking a look at off-ball orbital diagrams and electron configuration. Now, this definitely can be a more tedious and difficult concept to do. It requires a lot of practice, but it also is not easily explained within a 5 or 10 minute video. I will try to keep this as short as possible, but there are some parts of this, especially when you get to the noble gas abbreviations, the shortcuts, that might have to be in a second, more advanced video version of this topic. We're going to stick to the basics here. So we're going to show you how to do orbital diagrams as well as how to get the electron configuration from that. This video is meant to follow the previous video on Bohr models and Lewis dot diagrams because we can tie together all these different representations of the atom, and that is the point, to understand what information and what skills can we use with just a periodic table. So we're going to dive right into that. As you can see on the screen, we've already covered quite a number of topics already so far. So here is where we are today, drawing those off-ball diagrams and writing electron configurations from that. So first, what is an off-ball orbital diagram? Well, these are off-ball orbital diagrams. And this I have drawn on paper myself, but if you do a quick Google search for orbital diagrams, you'll see many different types of images that pop up. Some of them have a bunch of boxes all over the place. Some of them look like how I have, where you have a bunch of lines. But there are some things that you should always see, no matter which version you're looking at. One thing you'll always see should be some arrow pointing up, and it should be labeled as energy. Because what these diagrams are showing you is when you think back to the Bohr models that we were drawing in the previous video, we mentioned that these electrons are being placed in what is called energy levels. And so the idea behind this is that electrons are inhabiting different zones within the electron cloud based on how much energy they have. It is similar to thinking about staying in an apartment complex or a condominium, to where, depending on which floor you live on, that will determine your rent, how much money you will have to pay to stay there. Typically, the higher up that you're living, the more you probably have to pay. And if you look at the off-ball diagrams, that's the same thing that we see here. The higher up you go within the building or the diagram, if you will, the more energy that is required or associated with staying there. Now, the very nature of that energy and everything else that we do with that can come later. But for the purpose of this video, we want you to be able to complete or draw or fill in these diagrams, understand that the electrons in the higher upper levels have more energy, and then you want to use the diagram to create what's called the electron configuration. So let's look at one of the elements that we've done with the Bohr model so we can tie together how this can translate into the orbital diagram. So I'm going to use calcium because it has a good number of electrons. We did the Bohr model for calcium. It's element number 20, so it has 20 electrons. If you drew the Bohr model showing you where the electrons are, the only information you're getting from this is which energy level these electrons are living in. But as we saw from our discussions of the orbital diagrams, the level is not the only place for the electrons to live. Within that very level, which will be the rings here, is something called a sublevel. A similar analogy would be if you stay within an apartment building and you know which floor you're going to live on each floor there are rooms. That would be your sublevels. And then within a sublevel, we have what are called orbitals. That would be similar to living in a particular room in an apartment that's on a certain floor. So it kind of gets a little complicated, but if you think about living within an apartment building or some type of condo building, it can make sense. We want to understand not only which level these electrons are on, but which sub-level they're on, and then which individual part in that sub-level are they living on. Now, it doesn't easily translate from the Bohr model, and definitely you're not getting that information from a Lewis dot structure That's irrelevant at this point. But for the bar model, we only see the levels. We don't see the any other specific locations of these elements, of these electrons. So let's take a look at calcium first, which is element number 20 on the periodic table. Here it is right here in the second group. So we're going to map out the orbital diagram for the element calcium. And again, that is element number 20. So that means it has 20 electrons to be filled. Now, how do you fill these in? Well, you're hopefully already familiar with the rules on how to do this. And here are those three rules. The first is called the off-ball rule. It basically says when you put these electrons into their locations, the electrons must be placed in the lowest energy orbitals first. As I tell students, like Drake says, start from the bottom, now you're here. You will start way at the bottom in the lowest energy zone, which would be 1s, and then you work your way up the diagram. So you cannot just start throwing electrons in the higher level spots. You must start from the bottom. Now you get up there. That's called the off-ball rule. The second rule is called Hund's rule. It looks like it's a lot, but it's pretty simple. It says that an electron must occupy each orbital in a sublevel before you pair them up with more electrons. So that part means, if you notice, some of these positions have multiple lines to them. So this, for example, this 1s is just one line, 2s is just one line, but 2p has three. So these are three orbitals that can be filled in within the sublevel of 2p. So what we're saying is you must put an electron, one in each spot first before you double up. That is similar to how I had been drawing these Bohr models. Because for the Bohr models, I was putting one electron, and then I would go to the right, and then I would go down, and then I would go left, and then I would pair up. Just an analogy. But the way we do Bohr models does not mean how you're going to do these off-ball diagrams. But it is similar, and that's why I wanted to show that. So Hund's rule is put one in each spot before you pair up, and then we prefer that you have them pointing in the same direction when you're putting one in each spot. Now, when you do have to pair up, that's where the third and final rule comes into play, and that's called Pauli's exclusion principle. It says that the electrons must be paired with opposite spin. And so we're going to draw these electrons as arrows. So you'll see things like this all over your diagrams, or if you're one of the cool people, we do this, the one-sided arrow like so. So when you're putting electrons together within that same orbital, then you have to have them with the opposite spin. So you're going to see this as you practice this. This is a skill that must be practiced. You must practice this. There is no way that you can become good at this without actually doing it. So let's give it a try. We're going to fill in the orbital diagram for calcium, which is element number 20. So you're going to be drawing 20 electrons. The electrons will be drawn as arrows, not as circles. So start from the bottom. That's off-ball's rule. I'm going to draw my first electron pointing upwards. That's just what I do. You can start your first one down if you want. If you want to, doesn't matter, as long as you are consistent. So 20 electrons. Here's the first one. The second one, I must fill this before I move up. Again, that's off-ball's principle. Because there are two to go here, I'm pairing these two together. They must point in opposite directions. That is Pauli's exclusion principle. There's a total of 20. Let's continue. Once this area has been filled, the 1s, we go up to the next lowest energy place, which will be 2s. My first electron I'm going to put here, pointing up. That's electron number 3. And now electron number 4 is going to point down like so. All right. So now we're going to go to electron number 5. You must go to the next lowest energy zone, which is not 3s, it's 2p. It's drawn over here to the right. This zone has 3 orbitals that can be occupied. So for electron number 5, I'm going to put one arrow pointing up. For electron number 6, I am not putting that in that first box. Electron number 6 must go in the next orbital pointing upwards. Why is that? That's Hund's rule. You must put an electron in each orbital first before you double up. So we have a total of 20. Let's keep track of the numbers. We have 1 and 2, 3 and 4, 5, 6, 7. Now I can pair up with number 8 in the different direction, 9 and 10 electrons total. We're halfway there. Number 11, go to the next lowest place, which is here. 11, 12, now we're here at 3p, 13, 14, 15, now double up, 16, 17, 18, and then now continue to the last zone here, which is 19 and 20. Here is the completed orbital diagram for the element known as calcium. You have to make sure that you follow those 3 rules. It is a lot to know and learn. That's why you have to practice this skill over and over. So again, Off-Ball's rule says you must start from the bottom, then work your way up. Hund's rule says that if you have electrons going into multiple orbitals within a sublevel, for example 2p, you must put 1 in each orbital first before you're allowed to double up. And when you put that 1 in each spot, have them pointing in the same direction first. So as you saw, I always put my first arrow up. You can be different and point your first arrow down. It's your choice. So, and also too, if you have to pair electrons, which you see we did do here, that's going to be Pauli's exclusion rule or exclusion principle, which says your 2 electrons that are within the orbital must be pointing in opposing directions. So 1 arrow goes up and 1 goes down. Now, do electrons look like arrows in real life? Obviously not, no, okay? But we think of them more as a spherical particle, so they will be spinning, kind of like the moon going around the earth or the earth going around the sun, not arrows. So the question is why do we draw arrows? And that's because why not? So for the next example, let's look at another element that we've drawn the Bohr model for. And again, this is really good for you to compare how this Bohr model for calcium compares to the orbital diagram for calcium. 20 electrons, but 2 different ways to draw this. Let's look at this element, argon, which is element number 18. Actually, I'm going to do one that's a little, we'll start with 18 first. So argon is element number 18, so we're going to draw 18 arrows, starting from the bottom, which is whose rule? That's Off-Ball's rule. So here we go, 18. So here's number 1, number 2, number 3, number 4, number 5, 6, and 7. Hey, take this with you. I apologize. I'll have to edit this. Oh, she did not. Maybe, hopefully I can snip that out. I apologize for that. What, the other time? So we have 18 total. 1, 2, 3, 4, 5, 6, 7. Now double up. 8, 9, 10. Keep going upwards. 11, 12, 13, 14, 15. Now double up. 16, 17, and 18. So here is the completed diagram for element number 18, which is argon. Notice that I do have some positions available above where we left off, which would be the 3p zone. The reason why I did this is because this is not a really complicated skill where you have to learn how to do something different for each of the elements on the periodic table. Every element on the periodic table is going to have its electrons placed within the atom in the same way you see here. The lowest level electrons will be living in the zone called the 1s zone. That is a low energy position, and the actual 3D shape of the area that the electrons that can be there, that zone that they are able to actually fly within for the most part, has a spherical shape. Now, we're not actually going in depth into this in this entry level chemistry course, but the S does not stand for sphere, but you can kind of think of it that way. It is actually a spherical zone, kind of like a globe area. And those two electrons living in that on the first level are living and flying around and spinning around within this little circular area. So you have your nucleus of the atom, and then there is a sphere kind of around that, that these two electrons are buzzing around within that electron cloud. But that's just for these two. And as you go higher and higher, you have electrons that are living in other areas, other shapely areas, other energy levels, like 2s. 2s would be another zone a little bigger than that, also has a spherical shape, more energy. So you'll see the two electrons that are living in that area flying around within a different shape zone as well. And then that trend kind of continues as you go up the off-ball diagram. So we're just trying to understand where these electrons are. And as far as their energy goes, as well as their behavior, these will help you understand that. If I gave you an element with a little bit more than just 18, for example, element number 20, which was calcium, all I would do is add the extra 2. 18 was here, there's 20 here. I would add 2 more to get to 20, and the 2 extra ones would have to go in this spot, 4s, which gets you this. So the point is that there's only one way to draw these off-ball diagrams. All you have to do is get the number, 20 or 18 or whatever, and just fill in the arrows as you go up. You're going to do the same pattern no matter what the element is that you're asked to do. The exact same pattern. Even if I give you an element with a whole lot more than just 20, which is what we're going to do for the final example. So this will be a pretty tough one because, as you can see, I had to draw a diagram that is much, much larger than the 2 you saw above. Because if you're looking on the periodic table, we have elements with a lot more than just 20 electrons to it, okay? If you look especially towards the bottom at some of the newer created or synthesized elements, we have one with 117, 118. And in theory, there are probably elements in the universe that just go on for infinity. Now, does it? We don't know. I don't know. But theoretically, you can always add just one more electron. Instead of 18, 118, 119. Instead of 119, 120. If you understand how to do these diagrams, then it doesn't matter how many electrons we give you. You will always follow the 3 rules. Start from the bottom, now you're here. Start from the bottom, now you're here. 1 up if you have multiple orbitals, then pair up. And then when you pair up, opposite spin. So let's look at one of the largest elements on the periodic table that will require us to fill in a much larger orbital diagram. Let's try element number 100. Element number 100. The element that has an atomic number of 100 on the periodic table has a symbol Fm, and that is fermium, element number 100. So that means it has 100 protons, it has 100 electrons. All right? So I don't care what the element is. We got 100 arrows to draw. Let's follow the rules and let's do it. I suggest, if you can, to pause the video and to play it back when you have your answer. Not sure why my camera just went out like that. That was kind of weird. So again, so sorry if you didn't get to see that. We're going to do this for element number 100, which is fermium. It has a 100 protons, 100 electrons. Doesn't matter. We're going to put 100 arrows into the off-ball diagram, and we're going to do the same thing we did earlier. Whether it's 18 or 20 arrows, it doesn't matter. You still follow the 3 rules. Off-ball, which says to start from the bottom. Now you're here. Hund, which says for these multi-orbital zones, like the P's, and you see these weird ones that get up higher, you're going to put one in each spot first, pointing in the same direction, then double up. And then the last but not least, Pauli's exclusion principle, which says that if you do have to pair these up, put one facing in each direction. So one arrow up, one arrow down if they have to share an orbital space. I would pause the video and see if you can do the 100. And if you like, you can pause the video and redraw the diagram that I have, or you can do a quick Google search for an example worksheet that has a bunch of empty spaces. But I would pause this video, see if you can put the 100 in there, unpause, and then check your work. So let's do this together. 100, here we go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36, 37, 38, 39, 40, 41, 42, 43, 44, 45, 46, 47, 48, 49, 50, 51, 52, 53, 54, 55, 56, 57, 58, 59, 60, 61, 62, 63, 64, 65, 66, 67, 68, 69, 70, 71, 72, 73, 74, 75, 76, 77, 78, 79, 80, 81, 82, 83, 84, 85, 86. Ran out of room. So I can continue down here. That was, was that 86? Man, I hope so. I think that was 86. You can rewind the video back and check me. This continues. And if I gave you a worksheet, it would have the extra spots. I think you guys get the point by now. So that's just the first half. And orbital diagrams are pretty easy. And at this level of chemistry, we're not going to require you to create this diagram from scratch. We would typically give a student one that has the boxes or the lines there, and you would just fill them in. So now let's talk about the second half of this, which might be a little shorter, and that's called the electron configuration. Now, some of us consider these orbital diagrams to be like a map. It is showing you exactly where these electrons are living within the atom. Where's the structure? Like living in a home or a house or an apartment building. So these orbital diagrams will be the map to show me how the electrons are arranged. The electron configuration, however, would not be a map showing me where, but more of your address describing where. So for example, if I want to know where our school is, I could look at Google Maps to show me exactly where the school is located in the city. And that map would be useful for those who want to see a picture. However, some of us might want the address. So for example, the address to the school is going to be some number, a street name, city name, state, zip code, whatever. Your electron configuration is just that. It is a way to describe the picture of where the electrons are located. So these are two ways to do the exact same thing. Well, and if you consider Bohr models and Lewis dot structures, 4 ways to do the same thing, and that is understanding where the electrons are. And the question that should be the back of our minds is, why do we care so much about electrons? That's the whole point of this chemistry class. So let's look at electron configuration. If you do your off-ball diagrams, then to write the address, the electron configuration, it's pretty easy. What you will do is you will start from the bottom and you're going to tell me what level and then what sub-level you're in, and then how many arrows, which will be the electrons, how many electrons do you have in that zone? So for this element, number 20, which was calcium, the electron configuration will be written like this. Starting from the bottom, the first level we're on is 1, and it is the S sublevel. So the level is 1, the sublevel is S, and then how many electrons do we have in that 1s zone? There are 2 arrows drawn, so that makes a total of 2 electrons there. So the electron configuration will start off saying 1s2. Notice the level is written as a large number. The S, which represents sublevel, is written as a lowercase letter. And then the number of electrons looks like an exponent written above that to the top right, and that's a small number 2. Then you go up to the next area. So after 1s, we hit the second energy level, which is 2, and the sublevel I'm on right now is called S, and there's a total of 2 electrons drawn there. So 2s2 would be written next. After the 2s zone, you go to the 2p zone next. You're going up. Started from the bottom, now you're here. So for the second energy level, we're still there, but now we're in what's called the p sublevel. And there are 3 orbitals there, but how many electrons total? 2, 4, 6. So we're going to put a 6 there, 2p6. Continue. Next is energy level number 3. Sub-level is S. How many there? 2. Next, we're still on level number 3, but now we're in the P sub-level, and there's a total of 2, 4, 6. Now we're in level 4, sub-level S, 2. So this sequence would be your electron configuration. This is the map of where the electrons live. This is the address of where they are. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. How about we have you do this for the second example, which was, I believe this was element number 18, that's argon. Based on what we have drawn, what would the electron configuration be? Just as a hint, you will not be writing down anything for zones where there are no electrons. There were no electrons in 4s or beyond, so you don't have to go beyond that. Let's start it. 1s2, 2s2, 2p6, 3s2, 3p6. Stop. There are no more. So here is the electron configuration for argon. 1s2, 2s2, 2p6, 3s2, 3p6. Now, look at these 2 examples that we just did. This is for the element calcium. This is for the element argon. Compare and contrast their electron configurations. Calcium starts off with 1s2, so does argon. 2s2, argon has that as well. 2p6, same thing. 3s2, same thing. 3p6, same thing. Argon has 3p6 as well. The difference is that calcium has 2 extra electrons, and those 2 extra ones had to go into the 4s2 spot, whereas argon stops in 3p6. Argon has 18 electrons, calcium has 20. So what I want you to notice here is not only do the diagrams look similar to each other, except that calcium just had 2 extra, The electron configurations written here also look similar, except that calcium had just a little bit extra. For the most part, calcium's orbital diagram and calcium's electron configuration looks exactly like argon's, but with two extra electrons. As a very, very lazy chemist, we can use this to come up with a way to do an abbreviation or shorter version of this. And here's how it's going to work. We call this the noble gas abbreviation. As we will see how important having 8 valence electrons is going to be, and you can look back at the Bohr model videos or the Lewis dot diagram, or even here, looking at electrons that are in your outer shell, your outermost level. Here's our energy level 3. Energy level 3, we see 1, 2, 3, 4, 5, 6, 7, 8. Yeah, there is some other levels beyond there, but I'm looking at the highest level in argon, that's level 3, and there's a total of 8 here. So if you go back to the Bohr model discussions, argon was right here at the bottom. Here is the diagram for argon. So you see 1, 2, 3, 4, 5, 7, 8. 8 there. If you draw the Lewis, you see 8 here. 8 is a very, very important number in our universe. Number 8. If you turn it sideways, infinity. But that's a conspiracy. So, what's the deal with this? Noble gases and the number 8 are very important. Number 8 really isn't more important, not necessarily the noble gases, but it looks like calcium almost looks just like that noble gas, except that it has just a little bit extra. So how about this? Instead of having to draw or write all of this information, when we can see that calcium's information will look exactly like argon's information with just a little bit extra, and with argon being a noble gas that is stable, has 8 valence electrons, it's very nice, and everybody wants to be like it. We can actually use argon and the other noble gases as a shortcut tool. So what we do is when you look at any element on the periodic table, the noble gas that you will pass by on your way to creating whatever the element is you're talking about. So an example of calcium, if you're looking on the periodic table, if you go from left to right and then go down, you will pass by argon and then you will hit calcium because argon comes before calcium. Whatever noble gas you pass by first to your destination, you will put the symbol for that noble gas in brackets. Argon is Ar. So we're going to put the symbol for argon in brackets like this. And then pick up the rest of your electron configuration from there. In the case of calcium, calcium had everything that argon had up into the 3p6 point. And then after that, calcium had 2 extra ones at 4s2. So everything here is argon's information. What comes after argon? That 4s2 part. So for the noble gas abbreviation, argon, and then write 4s2. So instead of writing that 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, you could just put argon, 4s2. I'm done. There you go. That's it. That's called the noble gas abbreviation. There's a lot of things in chemistry that are about abbreviations and shortcuts, so we welcome that. So then, if you look at the large one before you wrap up, we had element number 100, and I did not even create enough spaces here to finish all of it. But let's pretend that we weren't going to do element number 100. Let's just stop at where I did end up, which I believe this was number 86. So then, and you can confirm this, I could be wrong. I would hate to be wrong because I'm not going to redo this whole entire video. But what element is element number 86? Well, looking at my periodic table, the element with 86 electrons is going to be over here, radon, number 86, radon. So atomic number is 86. So this diagram that I have drawn would be the orbital diagram for the element known as radon. 86 electrons. Here it is how it is filled in. Now, radon, if you notice, it's a noble gas. Can you use the noble gas abbreviation on a noble gas? Generally, we say no. I mean, because if you did, this is radon. Radon is a noble gas. So then you would do this. And done. And no, we don't want that. We want to see you write this stuff out. So it is good practice that what you would do is you'll go to the last noble gas before radon. So on the periodic table, the one that comes before radon is xenon, right above that. So you would be doing bracket xenon. And where does xenon end? Xenon is element number 54. So you might want to have to find the 54th arrow and then continue from there. What would that be? 54, what's that? 27. So we need to find 27 boxes. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Let's do it this way. 2, 4, 6, 8, 10. Did that wrong. 12, 14, 16, 18, 20, 22, 24, 26, 28, 32, 34, 36, 38, 40, 42. I already forgot where I was. 44, 46, 48, 50, 52, 54. So the 54th electron was here in 5p. So that would be xenon. And then we can pick up from there to get to 86, which is radon. So after 5p, then would come 6s2, 4f, and then he's like, what the heck? We just went from 6 to 4? Yeah. That is a total of 14. And then now you're in 5d with 10. And then you're at 6p, 2, 4, 6. So this would be the noble gas abbreviation for the noble gas, radon. It will use xenon's information and then pick it from there. And if I gave you an element that comes after radon, then you would use brackets Rn for radon and then whatever else comes after that. Okay? So I know that's a lot. This is definitely another one of those skills that takes a lot of practice, and I hope that at least shed a little bit more light on electron configurations and orbital diagrams. And practice makes perfect, so get to it.